This is a variation of the problem that I had you do on your first practice exam. And let's be careful. Notice that here we have an initial speed of 10 meters per second, which means at the top of the valley here, we're not only going to have gravitational energy, but also kinetic. And we want to know the speed of the car at the bottom of the valley. So let's be clear. We have mgh at the top plus 1 half mv at the top squared. And all of that's going to get converted into kinetic energy at the bottom of the valley. So our m's cancel once again. So we're going to have 10. And h at the top is 45 because that's the radius, plus 1 half. V at the top is 10, and we'll square that. And that's going to equal V at the bottom squared divided by 2. Continuing with our math, we're going to get, this is 450 plus 52, that's 500 equals VB squared over 2. Let me make sure this so 450 plus 50 is 500. So yeah, we're going to get 1,000 equals VB squared. And so this is going to end up giving me VB equal to, this will be around 33. Well, let's just double check. So when we calculate this out, it's going to be 31.6 meters per second. Which is awesome. All right. Now, we want to know the normal force on the car at the bottom of the valley if its mass is 1,000 kilograms. So, here we're going to have the normal force pointing up and the weight force pointing down. So we've got Fn minus Fg equal to mv squared divided by r. So Fn minus 1,000 times 10, that's mg, is going to equal 1,000. Now, we get v is 31.6, and when we square that, we're going to get 1,000 divided by our radius, which is 45. So when we actually isolate our normal force, we're going to end up getting the following as our answer. It's going to end up being actually, let's just simplify a little bit further. Times 1,000 plus, we're getting 32,222 newtons. We'll leave it like that. Honestly, I would write this as 32,200, but that's fine. We'll leave it like this. Now, assuming the car is going 60 meters per second at the bottom of the hill, we want to know the normal force on the car. It's a very similar calculation. So instead, we're going to have Fn minus 1,000 times 10 equals 1,000 times, now 60 times 60 is 3,600 divided by 45. And when we isolate the normal force, we're going to get a different answer here. Let's go ahead and calculate that. We're going to end up getting 90,000 newtons. So, assuming the car is going the speed at the bottom of the hill, we want to know what its speed is before it rolled into the valley. So at the bottom of the hill, we have all kinetic energy, and we want to know what was the speed it had at the top. So this is the energy that we have. Now let's get E kinetic at the bottom, which is going to be 1 half m v at the bottom squared equals 1 half m v at the top squared plus mg h. So we're going to have 1/2 times 1,000 times 60 squared plus 1/2 times 1,000 times v at the top squared plus 1,000 times 10 times the 45 at the top. Now notice the 1,000, the mass, cancels throughout all of this. So I'm going to end up getting 18,000 plus Vt squared over 2 equals, and I'm getting a mere 450 here. 60 times 60 is 3,600, sorry, that's 1,800. Sorry. Now, continuing this here, I'm going to end up getting 1,350 equals Vt squared over 2, or 2,700 equals Vt squared. So V at the top actually ends up being the square root of 2,700, which is 51.6, or about 52 meters per second. All right, so that's it for page 4.